In this homework, we want to be able to tell what type of function something is and also be able to be proficient at using domain and range. And we'll see it in a number of ways. First, in this first part, we're trying to find which of these four function types the function is, and then give an explanation for how we know. I'll do a couple examples here. This first one, and before I get started here, if you have not gone through and done this all yourself, stop this video, go and make sure you are able to do as much of this as you can by yourself, even if you can't do all of it before coming to the video. You never want to watch somebody else do math until you've done it yourself, because the learning is much worse. All right, this first one. The function type, what we're looking for is what kind of thing is going on in the equation. And we can really see what's going on with the x. Here we see that x is an exponent. We have something to the x power, and this is a constant. And really the rest of it doesn't matter very much. When you have something to the x power, there's going to be a constant multiplier because every time x goes up by 1, you'll multiply by an extra value of these. And so when there's an x as an exponent, it makes a constant multiplier, and the function type is exponential. And when I look at this, the key thing in this case was that x is an exponent. So anytime you have x as an exponent, you should be thinking exponential. All right, and this is the kind of explanation I'm looking for. All right, I'll do one table. So in tables, it takes a little bit more work than just looking at it. We know that tables that are linear have a constant rate of change. Tables that are quadratic have a constant second difference. Tables that are absolute value have two different constant rates of change, and then a exponential function has a constant multiplier. So that's kind of what we're looking for here. And so I usually start, if the x's are changing by the same amount each time, I start looking for a constant rate of change, or look at the rate of change to see what it is. It goes down by 2, down by 2, and then up by 2, up by 2, and this is that two constant rates of change, and so it's absolute value. And the explanation is there were two constant rates of change. We could be more specific than that if we want, but that's good enough. So we're looking for what is actually happening in the numbers to be able to tell us what's going on there. So this will require some analysis. Number 8 is interesting because it's not a full function. We only have a domain. The domain is x is greater than or equal to 0, or maybe 0 to infinity, something like that. But we don't have this part of the graph. And so it's difficult to tell if it's a quadratic, where it's got a parabola that comes back up, or maybe it's an exponential that goes down to 0. Because it's difficult to tell, we need to do some analysis on this. And what we're going to do is we are going to look, and just like we did with the tables, we're going to look to see is there a constant rate of change or what's going on. So a quadratic would have a constant second difference, and an exponential would have a constant multiplier. So let's look at the y values. Here the y value is 1. Here the y value is 2. Here the y value is 5. And here the y value is 10. I find exponential a little bit easier to look for than quadratic. So I'm looking for a constant multiplier, and this is times 2. But this is not times 2. But then this is times 2. So it almost looks like a constant multiplier except for this part right here. So let's see if it's quadratic. Here, instead of a multiplier, we're looking for the second difference. So here, going from 1 to 2 is adding 1. Going from 2 to 5 is adding 3. Going from 5 to 10 is adding 5. And these have a constant second difference of adding 2 each time. And because of that constant second difference, we can see this is quadratic. If we wanted to go backwards, so subtract 2 to get to 3, subtract 2 to get to 1, subtract 2 would be -1, and we can see that it would actually go back up if we go to the left, because the rate of change would be -1. All right, that's not necessary for you to know. So there's a constant second difference. The rate of change is changing at a constant rate. Okay, let's look at number 10 here. Lisa walks across the courtyard at a constant speed. So I should already be thinking either linear or absolute value, depending on what I'm measuring. What function measures her distance from Jaime, who is sitting on a bench halfway along her walk. So she's like, so here's Jaime, you know, I don't know. He's sitting on a bench, and this is halfway along her walk. So here's Lisa, and she's walking. Okay. And so we're looking for her distance and from him. So here's Jaime, and it's her distance from Jaime. And her distance is going down at a constant rate as she gets closer to him. And then it goes back up at a constant rate. And so her distance goes down and then goes back up. If this had been like measuring her distance from like a person over here, it would have just been a constant rate of change because she's just getting further and further away from him. That would be linear. But in this case, it's absolute value because there is, so absolute value, and it's because there is a constant rate of decrease, then a constant rate of increase, because what we're measuring is her distance from Jaime, and her distance from Jaime is going down at a constant rate and then up at a constant rate because she's walking at a constant rate. All right, let's look at the back. In part 2, we need to decide whether something is discrete or continuous, and then state the domain and range in as many ways as we can. So let's look at this first one. This is a table, and there's no extra information. This is all we have for this function, and since this is all we have, there are only individual points. There is no x value at 2.5 that we can tell the y value of. Like, what is the y value at 2.5? I don't know. And it's not mentioned here. And because it's not mentioned and it's not defined, all the in-between values aren't defined. This is discrete. I'm just going to circle it. I guess I could write it down here. And so when it's discrete, we have to use set notation where we just list out all the possible x values. The domain is the set of all x values that are defined. And those x values are 2, 3, 4, 5, and 6. The range is the set of all possible y values, and I'm going to write the wrong answer first. It is not 8, 6, 4, 6, 8. This is wrong for 2 reasons. The first reason is we don't need to repeat values. We're just saying, like, what are the output values? And the output values are just 4, 6, and 8. And the second thing is we go from smallest to highest. So we can fix this by just getting rid of this 8 and this 6 here, and then this would be correct. The y values are 4, 6, and 8, and we always start with the lowest and go to the highest. Let's look at a different table. Here's a table, but this time there's more information. They tell us the function is y equals 5x with only some of the values given, which is what a table always is. It only gives us certain values. But that doesn't mean that these are all of the values. This is the function. These are just some of the values. I could add on and do 5, 25. I could do like 2.5, and I could know that the y value would be 12.5 because that's 5 times the x. And so all of these in-between values make sense. So because I have this additional equation to help me find, it defines more x values, I know what all the in-between x values will give me. And so this is a continuous function, even though it's a table, because all of the in-between x values make sense. The domain. I need to think of what are all the possible x values I can put in here. And there isn't anything I'm not allowed to multiply by 5. So there are 3 ways I can write this. The first way is we can say all real numbers, and this is the symbol for all real numbers. It's an R with a double line at the beginning. We can say in interval notation, all the numbers between negative infinity and infinity with parentheses, because we never actually get to infinity. They aren't numbers that can be plugged in for x. These are not x values you can plug in. 5 times infinity doesn't make sense. And the last thing is we can write it in set notation where we can say negative infinity is less than x is less than infinity. Oops, I need braces there. If you left off the braces here, you wouldn't lose points. So the x values are all the numbers between negative infinity and infinity, and these are 2 ways of writing that. And it's the same thing for the range, although this would be a y instead of an x. All right, 2 more, I think. Let's see, we have a graph. This graph does not have the in-between y values or x values. There are these missing spaces here. And because there aren't in-between values that are defined, like it would be if there was a line, if there were a line, this would be defined. This is a discrete function because we don't have, for instance, negative 1.5 as an x value. There's no y value that goes with it. So anytime we're missing in between y values, it's discrete, which means we need to use our set notation and just list them out. We always go from smallest to biggest, and the smallest x value is negative 2. The next smallest x value that is defined is negative 1, then 0, then 1. And it has this arrow at the end, which means this pattern will keep going. 3, 4, and we put a dot, dot, dot to show that it's going to keep going. The y values you might think are 2, 0, negative 2, whatever, but that doesn't start from smallest to lowest. For y values, we always start from lowest to smallest, but there's this arrow at the end, which means the y's are going to keep going down. So we actually are going to start with a dot, dot, dot at the beginning, because the smallest y value is going to keep being smaller over here. And I'm going to put y values of negative 4, negative 2, there's a y value of 0 here, and a y value of 2. And that's the highest y value, and so I can close my braces. So the x values go between negative 2 and infinity, and the y values go between negative infinity and 2. The x values don't skip any integers. The y values are all the even integers, but all of them are, both of them are discrete because there aren't the in-between x or y values. Let's look at number 10. Okay, so there's some high school where there's a function c of p equals 3p. It's the number of cell phones as a function of the number of people at the school. So the first thing I want to think about is the x value here, the independent variable is people. And so is this discrete or continuous? Can you have like 3.7 people? No, so the in-between values won't make sense, and so this will be discrete. What is the domain? So the domain, since it's discrete, I'm just going to list them out. What is the lowest number of people that you can have to make sense in this situation where we can find out how many cell phones there will be? And the lowest number is 0. You can't have negative people. It's always a good idea to consider negatives. And in this case, negative people having negative cell phones doesn't really have any real world meaning. So you can have 0 people. The next highest number of people you can have is 1, 2, 3, dot, 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 because there isn't a clear maximum number of people at this high school. The range, if there are 0 people in the school, there would be 0 cell phones. If there's 1 person in the school, 3 times 1 would give us 3. If there are 2 people in the school, you would have 6, 9. And we can see that the output values are all multiples of 3. You're never going to have like 44 cell phones because there isn't 3 times a whole number of people that would have 44 cell phones. So these are the possible output values for the model. And I hope that helped and the rest of your homework goes well.